Welcome back to the deep dive. We are doing something a little different today. Usually we scour the internet, we pull a whole stack of papers, and we pick a topic that we think you need to know about.
Yeah.
But today, the topic picked us.
It really did. It came directly from the mailbag, and honestly, it's one of those questions that just stops you in your tracks.
Yeah.
It sounds so simple, but the answer just it explodes into this fractal of complexity.
Exactly. The listener asked a very specific question, and they gave us a very specific deadline. They asked, will we have a Dyson Sphere or a Dyson Swarm in the next 5 years?
Talk about putting pressure on the engineering department. 5 years.
Right. I mean, that's 2031. So I want to start by just addressing that head on. If you're the person who wrote in and you're asking, will humanity have a completed megastructure, a full-on shell encasing the sun, capturing 100% of its energy by the time I need to renew my passport?
Then the answer is a hard, definitive, unambiguous no.
Absolutely not.
Definitely no. We are currently a type 0.7 civilization on the Kardashev scale. I mean, think about that. We are still burning dead dinosaurs and arguing about wind turbines.
Yeah, we're not exactly wrapping a star in metal next Tuesday.
Not even close.
But, and this is why we're doing this deep dive, if you actually dig into the papers, if you look at the recent experiments coming out of places like Caltech and the astronomical surveys happening right now, the answer gets, well, it gets a lot more nuanced.
It does, because while we aren't finishing the sphere, we are absolutely seeing the first sort of fledgling steps of the technology you would need to build one.
Right.
In fact, I think we might look back at this exact 5-year window as the moment the concept moved from, sci-fi dream to actual engineering roadmap.
You're thinking it may peel, aren't you?
I am. The microwave array for power transfer low orbit experiment, it's a bit of a mouthful.
I bet, yeah.
But what happened earlier this year was genuinely historic. They successfully beamed solar energy from a satellite in orbit all the way down to a receiver on Earth.
Wireless power.
Yeah.
From space.
Exactly. Now, it wasn't a massive amount of power. You couldn't run a city on it, not yet. But it proved the physics works. Outside the lab, in the real world.
So you collect energy in the vacuum, you convert it, and you beam it where it needs to go.
That's it. That is the fundamental building block. It is the single Lego brick of a Dyson Swarm.
So the 5-year answer isn't about the finished product at all. It's about the toolkit. We're actually building the tools right now.
Precisely. Look at what's happening. We have reusable rockets that are just crushing launch costs. We have autonomous robotics getting smarter every single day. We have this new wireless power transmission. The question isn't, is it possible anymore? The question is, what's the scale?
And that is the mission for today's deep dive. We're going to scale this all the way up. We're going to unpack what a Dyson Sphere actually is, because I guarantee the picture you have in your head is probably wrong.
It almost always is.
Then we're going to look at the mega engineering plan to build one, which, I mean, it involves a project so aggressive it makes the pyramids look like a sandcastle. We are literally talking about dismantling an entire planet.
Yeah. Sorry, Mercury.
And finally, we're going to look at the search. Because even if we don't build one in 5 years, there is a very real non-zero chance that we might find one in the next 5 years.
We are absolutely in the golden age of looking for technosignatures. If they are out there, we have the best chance in human history of spotting them right now.
Okay, so let's get into the stack. We've got Freeman Dyson's original 1960 paper. We've got technical papers on orbital mechanics. We even have Reddit threads that go into, frankly, frightening detail about mining logistics. But let's start with the basics, the definition. What exactly is a Dyson Sphere?
So the concept formally enters the scientific conversation in 1960. Freeman Dyson, who is just a legendary physicist, writes this paper with a very dry title.
Very academic.
It was called Search for Artificial Stellar Sources of Infrared Radiation.
Which is really just a very polite way of saying how to find aliens.
It is. But Dyson was always very clear about one thing. He didn't invent the idea. He was very upfront that he borrowed it from a 1937 science fiction novel called Startmaker by an author named Olaf Stapledon.
I love that. The science is directly following the fiction.
Always. In Startmaker, the author describes this vision of a galaxy where every single star is surrounded by a gauze of light traps. The idea was that these advanced civilizations had grown so hungry for energy that they had to catch every last photon their star emitted.
They couldn't afford to waste any of it.
Not a drop. And Dyson read that, and he looked at the thermodynamics of it all and said, this isn't just a good story, this is inevitable.
Inevitable. That's a really strong word.
Well, think about the math of growth. If any technological civilization survives long enough, its energy needs just grow exponentially.
Hmm.
A 2% growth in energy use per year doesn't sound like much,
I
right?
know, it sounds manageable.
But you compound that over a few thousand years and you completely exhaust your home planet's entire energy budget.
You run out of coal, you run out of oil, you run out of uranium.
You run out of everything. The wind, the tides, geothermal, it's all just a drop in the bucket. The only real power source left is the star itself. I mean, our sun pumps out 3.8 times 10 to the 26th watts of energy every single second.
A number so big it's meaningless.
It is. And we use a tiny, tiny, tiny fraction of 1% of that. Almost all of it just streams past Earth into the void. It's wasted.
So a Dyson sphere is just a bucket to catch all that wasted energy.
It's the ultimate bucket. It captures the entire output of the star. And doing that is what pushes you from a Type I civilization, one that uses the energy of its planet, to a full-fledged Type II civilization.
Okay, so that's the why. That makes sense. But this is where the what gets really tricky. Because when I say the words Dyson sphere, I immediately picture that episode of Star Trek, The Next Generation.
Of course, relics.
Exactly. Scotty is found and they find this massive solid metal shell. It's like a hollow ball. The sun is in the middle, and on the inside surface of the ball, there are continents and oceans and a whole world.
Right. And I hate to be the bearer of bad news for every sci-fi fan out there, but that structure, it is physically impossible.
Okay, now, impossible is a big word in physics. Do you mean we can't build it yet, or do you mean the universe literally doesn't allow it?
I mean, the universe effectively forbids it. And Freeman Dyson himself was apparently really frustrated by this misconception his whole life. He always wished he'd called it a biosphere or a swarm instead.
Because the solid shell fails.
It fails on two completely fundamental levels.
All right, let's break them down. What's the first problem?
The first is the material strength problem. So imagine you build this giant shell around the sun at the distance of Earth's orbit. That's 1 astronomical unit, or AU. It's huge.
Unimaginably huge.
Now, if you want people to walk around on the inside surface, like in Star Trek, you need gravity. But the sun's gravity at that distance is way too weak to hold you down to the shell. You'd just float off.
So you need to create artificial gravity.
Right. And the easiest way to do that is to spin the shell. You turn the whole thing into a giant centrifuge.
Okay, that makes sense.
But think about the forces involved. If you spin a structure that is almost 300 million kilometers wide, fast enough to create 1 g of gravity on the inside, the stress on the equator of that structure is it's astronomical.
One of the papers we looked at put a number on it. I think it was 10 to the 20th pascals.
Yes. And to put that number in perspective for you, that is millions of times stronger than the bonds holding a diamond together.
Millions.
There is no known chemical bond in the universe, no carbon nanotube, no graphene, nothing that could possibly withstand that force. The shell would just rip itself apart instantly.
So unless we invent unobtainium from the movie Avatar or some other kind of magic,
Or Clarkitech, as they call it.
right, unless we have magic, the spinning shell is out.
It's completely out. And even if you did have that magic material, you immediately run into the second and maybe even weirder problem, Newton's shell theorem.
This one is a lot less intuitive.
It really is. The shell theorem basically states that if you have a spherically symmetric body, like a planet or a star, it affects things outside of it as if all its mass were concentrated at a single point in its center. That's pretty straightforward.
Okay, that's how orbits work.
Exactly. But, and this is the absolute kicker, if you are inside a hollow spherical shell, the net gravitational force exerted by that shell on you is 0.
0.
It all cancels out. The pull from the bits of shell close to you is perfectly balanced by the pull from all the bits of shell far away from you.
Okay. But what does that mean for the star in the middle?
Well, it works both ways. The shell exerts no net force on the star, and
Yeah.
crucially, the star exerts no net force to keep the shell centered.
Wait, unpack that for me. The sun doesn't pull on the shell to keep it in place.
Not in a way that stabilizes it. The gravitational pull from the side of the shell nearest to the sun is stronger, yes, but the side of the shell also has less mass from the sun's perspective. The farther side has more mass, but the pull is weaker, and it just perfectly cancels out.
So the shell is effectively weightless relative to the star.
That's a great way to put it. The system is what we call neutrally stable. There is no restoring force. There's nothing pulling it back to the middle.
So if something bumps it.
If a big comet hits it, or if Jupiter passes by and gives it a little gravitational tug, the shell starts to drift.
And it doesn't stop.
It doesn't stop. Since the sun isn't pulling it back to the center, the shell just keeps drifting until one side of it crashes right into the surface of the star.
That feels like a catastrophic design flaw.
It's about as bad as it gets. To prevent that, you would need massive active propulsion systems. We're talking giant rocket engines firing constantly, 24/7, just to keep the sun in the middle of the room. It would be wildly inefficient.
So, okay.
Yeah.
The solid ball is a death trap. Freeman Dyson never actually proposed that. So what did he propose?
He proposed a swarm. Not one single monolithic object, but a vast collection of independent objects.
Like satellites. Billions of them.
Exactly. Imagine a cloud, a beehive of a billion individual satellites. Some of them are solar collectors, some are habitats where people live, some are just giant mirrors. And they're all orbiting the sun in these dense, complex formations.
And this solves both of the physics problems.
Completely. First, because each satellite is in its own independent orbit, gravity works perfectly. It's just normal orbital mechanics. And second, you don't need any super strong materials because you're not building one structure spanning millions of miles.
You're just building millions of individual space stations.
Exactly. Which is still hard, but it's an engineering problem, not a break the laws of physics problem.
And crucially for our listeners' timeline question,
Yeah.
you don't have to build it all at once.
That is the most important part. A solid shell is completely useless until it's 100% finished. If you build half a shell, the air leaks out, it doesn't work.
Right.
But a swarm, the very first satellite you launch, starts giving you energy. The second one doubles it. The third one triples it. It's modular. It's incremental. You get a return on your investment from day one.
Now, in the stack of papers, there was a variation on the swarm that I found absolutely fascinating, the Dyson bubble. And this uses something called statites.
Ah, yes. Statites. It's a made-up word, a portmanteau of static and satellites.
Which just sounds like a complete oxymoron. If you're static in space, you fall into whatever you're near.
Normally, yes. Orbit is really just you're falling sideways so fast that you keep missing the ground. That's all it is. But a statite cheats.
Ow.
It uses a solar sail, a giant, ultra-thin, perfectly reflective mirror.
And that's to catch the solar wind, right?
That's a common misconception. The solar wind, the stream of charged particles, does push on it, but that force is tiny. The real push comes from photon pressure.
From light itself.
From light itself. Light has momentum. It's a fundamental aspect of physics. So when sunlight hits that giant mirror, it pushes on it. Now you have two forces at play. You have gravity pulling the statite in toward the sun, but you have the pressure of the sunlight pushing the statite out.
It's a tug of war.
It's a perfect tug of war. And if you design it just right, if you make your sail big enough and your satellite light enough, the outward push of the light can perfectly cancel out the inward pull of gravity. The net force becomes zero.
So it just hovers without orbiting.
It hovers, it levitates. You could park a statite right over the sun's north pole, and it would just hang there, stationary, floating on a constant beam of light.
That is such a cool visual. A glittering, silent bubble of stationary mirrors just surrounding a star.
It's incredibly elegant. There are no collisions to worry about, no chaotic orbital mechanics to manage, just a static envelope of light collectors. It's beautiful.
Okay, so we have the design. We want a swarm or maybe a bubble. But now we have to talk about the elephant in the room. The sheer mind-boggling amount of stuff you would need to build it.
The mass budget.
The mass budget, yeah. One of the papers we read estimated that to build a swarm capable of intercepting a decent chunk of the sun's energy, you'd need about 10 to the 22nd kilograms of material.
Which is a number so big it's basically meaningless to the human brain. It's just a bunch of zeros.
Right. So to put that into context, you can actually visualize. That is roughly the total mass of the planet Mercury.
Give or take a few large asteroid belts, yeah.
So obviously we can't use Earth. We kind of need Earth for, living on.
Correct. Rule number 1 of mega engineering. Do not dismantle the biosphere. It's generally frowned upon.
So the plan, and this is discussed with a very straight face in the engineering literature, which is what I love about it, is to dismantle Mercury.
It is the only logical choice.
Logical. We're talking about eating a planet.
Well, just look at the specs for a second. Mercury is essentially a prepackaged construction kit just sitting there. It's surprisingly dense. About 70% of its mass is its iron-nickel core. It has silicates. It's got everything you need to build solar mirrors, structural frames, electronics.
And it's all about location, location, location.
It's right next to the sun. The solar flux there is 4 to 10 times stronger than it is here at Earth. That means you have massive energy availability for all of your mining operations. Plus, Mercury has virtually no atmosphere and very low gravity.
Which makes launching all that material off the surface incredibly cheap, energetically speaking.
Incredibly cheap. You don't have to fight a thick atmosphere or a deep gravity well. It's the perfect place to start.
Okay, I'm sold on the where.
Mm.
But the how is where this whole thing gets into, like, Michael Bay movie territory. The Reddit threads we dove into describe this as the bucket of lava approach.
It's actually quite brilliant in its brutality. You don't bother with delicate mining shafts or tunneling. You set up massive solar mirrors in orbit to focus sunlight onto the surface of Mercury.
You just melt the crust.
You turn vast swaths of the surface into a magma ocean. Then you have these automated machines that just scoop up the lava. You don't need to crush rocks. The heat has already done the work for you. You can use that heat to start separating the elements. The iron goes here, the oxygen goes there.
And then you have to get all that refined material into orbit.
Yeah.
But you're not using rockets.
God, no, rockets are way too inefficient for this scale. You'd use mass drivers.
Right. Railguns.
Exactly. Think of a giant electromagnetic railgun, kilometers long, built on the surface. Because there's no air resistance to worry about, you can just load a payload of, say, refined metal foil and accelerate it to escape velocity. Thwump, thwump, thwump. A constant, steady stream of material shooting up into space.
This is incredible. But it brings us right back to the central timeline question. The listener asks, can this happen in the next 5 years?
And here's the core of the answer. The construction method doesn't rely on us shipping a planet's worth of material from Earth. It relies on an exponential feedback loop. This is the absolute key to understanding the timeline.
Okay, walk us through that loop, step by step.
So we don't build the sphere builds itself. Step 1, we launch a seed factory from Earth. Maybe it's just one ship. Maybe it contains one mining robot, one fabricator to build solar collectors, and one small mass driver.
Okay, one ship. We can do that. That's plausible.
Step 2, the seed factory lands on Mercury. It starts mining enough iron and silicon to build one solar collector satellite. It fabricates it and launches it into orbit with its little mass driver.
Okay, step 3.
That new satellite unfolds its mirror in space. It starts collecting sunlight. And what does it do with that power? It beams it back down to the seed factory on the surface of Mercury.
Ah, so now the factory has more juice to work with.
Exactly. Now it has twice the power, so it can mine faster. Maybe it builds a second robot, a copy of itself. Now you have 2 robots building collectors. They launch 2 more. Now you have 4 units of power being beamed down, then 8, then 16, then 32.
It's a virus. It's an industrial virus that eats a planet.
It's industrial geometric progression. And this is where the timeline gets shocking. The Oxford researchers, a couple of guys named Sandberg and Armstrong, they actually ran the numbers on this. They modeled this feedback loop.
And what did they find?
They estimated that once you get that loop running, once the seed is successfully planted, you could disassemble the entire planet of Mercury in as little as 31 to 40 years.
That is terrifyingly fast.
Yeah.
4 decades to erase a planet from the solar system.
If you push the feedback loop to its absolute physical limits, yes. But, and this is the bid reality check for the 5-year question, that 40-year clock only starts ticking after we launch the seed.
And we don't have the seed.
We do not have the seed. We don't have fully autonomous, self-replicating robotics that can work in the harsh environment of space. We don't have the industrial-scale mass drivers. We have the concepts, like the May-Pili experiment proved, but we lack the integration and the scale.
So the final verdict is, we won't have the finished sphere in 5 years. But if we did have the seed technology today, we could theoretically finish the entire project within a single human lifetime.
Which is mind-blowing when you think about it. This isn't some million-year evolutionary project for a distant future species. It's a start it when you're 20 and cut the ribbon at your retirement party kind of project.
Before we move on from the construction, I have to ask about one specific detail from the mining plan that I just loved.
Yeah.
The problem of waste heat.
Oh, yes. The droplet radiators.
Tell us about them. Because if you are melting a planet's surface and running massive railguns, you are generating an insane amount of waste heat. And Mercury is already incredibly hot. How do you keep your robots from just melting into puddles?
You can't use fans, obviously. There's no air. You can't just use big metal heat sinks because they would saturate almost instantly. So the proposed solution is to use liquid metal as a coolant, something like tin or maybe gallium.
Okay.
You run this liquid metal through your machines, through the mining bots and the mass drivers, and it absorbs all that waste heat.
And then what do you do with the hot liquid metal?
Then you spray it out into space. You create a fountain, a massive arc of glowing liquid metal droplets. These droplets fly through the cold vacuum on a long ballistic trajectory.
And as they fly, they radiate their heat away.
They radiate their heat away into the blackness of space. Then, kilometers away, a collector dish catches the now cooled droplets and cycles them back into the system to be used again.
A fountain of glowing metal in the silent void. I mean, the aesthetics of this entire project are just on another level.
It's planetary butchery with a certain flair.
So, okay, we've done it. We've eaten Mercury. We have a swarm of billions of mirrors and habitats orbiting the sun. We are now generating 10 to the 26 watts of power. So we have to ask the ultimate question, why?
Why do we need that much juice? What's the point?
Yeah, I mean, free charging from my phone for eternity is great, but this does seem a little excessive.
The most basic driver is usually assumed to be carrying capacity. If you want to support a population of, say, quadrillions of humans or post-humans or their AI descendants, you need that kind of energy budget just to keep the lights on and run the life support.
Okay, so just more room for more people.
And that's the simple answer. But the really specialized applications, what you might call the killer apps for a Dyson sphere, that's where it gets truly wild.
And the outline we put together mentions the Matrioshka brain.
This is my absolute favorite concept in all of theoretical engineering. It's a computer the size of an entire solar system. It was proposed by a guy named Robert Bradbury, and it takes the Dyson Swarm idea and adds layers. Think of those Russian nesting dolls, Matryoshkas.
So it's a sphere inside a sphere inside a sphere.
Exactly. Here's how it works. You have your inner shell of computers right up close to the star. They're running incredibly hot, doing the most intense high-energy calculations possible. They consume the raw sunlight, they do their math, and they radiate waste heat.
Right, the second law of thermodynamics again. You can't get rid of the heat, it has to go somewhere.
But you don't have to waste it, you can use it. You build a second, larger shell of computers around the first one. This second shell is designed to absorb the waste heat from the inner shell. It uses that lower-grade heat energy to run its own computations at a slightly lower energy state.
And then it radiates even cooler waste heat.
Which is then captured by a third shell and a fourth shell and so on. You build layer after layer all the way out until the outermost shell is radiating heat at just a few degrees above absolute zero. You are squeezing every single ounce of computational utility out of every photon that left the star.
And what do you do with a computer that powerful? What's the point?
The point is everything. You could simulate entire universes with perfect fidelity. You could upload the consciousness of every single being in your civilization into a virtual paradise that's indistinguishable from reality. You solve the grand unified theory of physics. It is intelligence amplification on a cosmic scale.
So the Dyson sphere isn't just a power plant, it could be a digital heaven.
Or a really, really high-end gaming PC. It really just depends on your civilization's priorities.
Then there's the other major application, which feels a bit more vehicular, the idea of actually moving the entire solar system.
The stellar engine, or more specifically, the Shkadov thruster.
This is where we literally turn our sun into a giant spaceship.
Yeah, that's the idea. So a normal Dyson sphere, or swarm, surrounds the whole star to collect all the energy. But what if you only built a hemishell, a giant mirror that only covers half the star?
Okay, so you're just reflecting half the light, but where does it go?
It gets reflected back at the sun. Now, we know light carries momentum. It's a tiny amount, but it's there. If you reflect half of the sun's light back onto itself, you are effectively pushing against the star with its own light.
But wouldn't the mirror just get pushed away?
No, because the sun's gravity is pulling the mirror in. So the mirror hovers in a stable position where the light pressure pushing out equals the gravity pulling in. But the star feels an unbalanced force. The net effect is that the entire system, the sun, the mirror, and all the planets being dragged along by the sun's gravity, starts to accelerate in one direction.
You're driving the solar system through the galaxy.
Very, very slowly, but steadily. Over millions of years, you could steer your home star system across the galaxy. Maybe you want to escape a nearby star that's about to go supernova. Maybe you want to avoid a collision with another star system or a rogue black hole.
Or maybe you just want to move to a better neighborhood. Honey, pack up the planets. We're moving to the Alpha Centauri district.
It gives a civilization true cosmic mobility. You are no longer stuck in the cosmic crib where you were born.
But there's always a but. We have to talk about the dark side of this. The source material brought up something called the Nicole Dyson beam. And this connects directly to the Fermi paradox, to why we might not be seeing these things everywhere.
Yes, this is the inevitable weaponization of the swarm.
So how does that work? How do you turn a power plant into a weapon?
Well, imagine you have those millions or billions of independent mirrors in your swarm. You can use them to collect power for your Matrioshka brain, sure, but you can also use them as a phased array.
Like a phased array radar.
Exactly like that. You can coordinate them with incredible precision to focus all of that reflected sunlight or all the energy from lasers powered by that sunlight into a single, coherent, incredibly powerful beam.
And you aim that beam at what exactly?
You aim it at anything you don't like, an enemy fleet, an asteroid on a collision course, or a planet across the galaxy.
And what happens to that planet when the beam hits it?
With the focused power of an entire star behind it, you could boil its oceans from light years away, you could sterilize its surface, scour it clean of all life, you wouldn't even see it coming. The light from the beam travels at the speed of light, so the first sign you'd have that you are under attack is the moment your atmosphere ignites.
That is genuinely terrifying.
It is. And it provides a potential solution to the Fermi paradox, the great question of where is everybody? This is the dark forest theory. Maybe civilizations don't build giant, obvious Dyson spheres, or if they do, they hide them very carefully.
Because building one makes you a target.
Or it makes you a threat. The moment you start building a swarm, you are also building a gun and pointing it at the head of every other civilization in the galaxy.
So maybe your galactic neighbors decide to take you out preemptively before you can finish construction. Or you build it, but you paint it black so no one can see it.
You run it cold, you make it as stealthy as possible, you keep very, very quiet, you don't let anyone know you're home.
Which brings us perfectly to the final section of this deep dive, the search. If these things are so huge, and if they have to radiate so much heat, shouldn't we be able to see them?
We absolutely should, and that's the primary way we're looking for them right now. Infrared signatures.
This goes all the way back to Freeman Dyson's original 1960 paper. Energy is conserved.
It's the one law you can't break. You can wrap a star in a giant computer. The computer uses the starlight, does its calculations, but thermodynamics dictates that all that energy has to eventually leave the system in the form of low-grade heat, waste heat.
So a Dyson sphere won't look like a star in visible light. It might be completely dark, but in the infrared spectrum, it should glow like a Christmas tree.
It should be one of the brightest objects in the sky at certain infrared wavelengths. So we're looking for things that are strangely dim to our eyes, but incredibly bright to our heat-sensing telescopes. We're looking for that mid-infrared excess.
We're basically looking for the trash heat of a galactic civilization.
That's a perfect way to put it. We're cosmic dumpster diving for alien heat signatures.
Have we found any?
We have found candidates. There's a big search going on right now called Project Hephaestus. They took data from two major space telescopes, Gaia, which maps the precise positions and brightness of stars, and WISE, which is an infrared telescope, and they cross-referenced them.
For how many stars?
They analyzed about 5 million stars in our local neighborhood.
And what did they find out of those 5 million?
They found seven candidates that fit the initial profile. These are mostly M-dwarf stars, smaller than our sun, that have this weird, unexplained infrared glow.
7. I mean, that sounds incredibly promising. That feels like a we could find one in the next 5 years kind of discovery.
It does, but, and you knew there was a but coming. We have to be the scientific buzzkill here. The papers indicate that most, if not all of these, are likely to be false positives.
So what can look like an alien megastructure but isn't?
The number one culprit is dust. Usually they're things called hot dust dogs, which is a terrible name.
It is, yeah.
They're basically distant galaxies that are full of hot dust, and they just happen to sit right behind the star we're looking at from our perspective on Earth. The light gets blended together. Or sometimes it's just a very young star that still has a big, hot protoplanetary disk of gas and dust around it.
And there was a specific example from the search, Candidate G. We got really excited about that one.
They did. Candidate G looked perfect on paper. It had the right amount of infrared excess. It was around a stable star. But then they did a follow-up observation. They pointed a radio telescope at it, and they realized the weird signal wasn't actually coming from the star itself.
Where was it coming from?
It was coming from a background active galactic nucleus, a supermassive black hole at the center of a galaxy millions of light years behind the star. It was a cosmic photobomb.
It was photobombing the data. Wow.
Exactly. So, for now, no confirmed aliens.
But there's another theory, this one from Avi Loeb,
Yeah.
about why we might not be seeing these perfect glowing spheres. He calls it the fishing net theory.
The idea of aging spheres, I love
Yeah.
this.
Imagine a civilization builds a perfect Dyson sphere and then they die out or they get bored and move on. The sphere is abandoned. What happens to it over billions of years?
It gets hit by things. Micrometeoroids, comets.
Right. It gets riddled with holes. It slowly degrades and falls apart. It turns into a tattered, leaky fishing net.
It would still block a lot of light, but not all of it.
Exactly. It would let some light through, but it would block some. And because it's rotating and have all these holes, it would create these weird, erratic, flickering patterns in the star's light. Not periodic like a planet, but
Yeah.
chaotic.
And Loba has speculated that we might have already seen a piece of one of these broken nets.
He has. He speculates about Oumuamua. You remember that bizarre interstellar object that zipped through our solar system back in 2017?
Oh, yeah. The long, thin, cigar-shaped thing. Everyone said it had to be a comet, but it had no cometary tail, no outgassing.
And it accelerated away from the sun in a way that gravity alone couldn't explain. Loeb's speculative hypothesis was that it could be a shard, a tiny piece of a broken Dyson sphere light sail.
Because it was so thin and reflective.
It was being pushed by sunlight, just like a statite. It's wildly speculative, of course, but it fits the profile of the kind of space junk you'd expect to find from a Type 2 civilization.
That is a haunting image. The idea that we're just drifting through a galaxy that's littered with the broken shards of ancient, dead power plants.
It's archaeology on a galactic scale.
And it completely changes what we should be looking for. Maybe we shouldn't be looking for the perfect, shining, brand new sphere. Maybe we should be looking for the ruins.
So let's bring it all back home. Back to the listener's original question. Will we have a Dyson sphere in 5 years?
The short answer is still definitively no. We lack the self-replicating robotics. We lack the political will to dismantle Mercury, which, let's be honest, is a pretty hard sell at the UN.
Yeah, that's a tough vote.
And most importantly, we lack the immediate need. We don't need 10 to the 26th watts of power. Not yet.
But what's the nuanced final answer?
The nuanced answer is that the fundamental concepts are active science right now. We are beaming power from space. We are designing and launching solar sails. We are scanning the skies with the James Webb Space Telescope, which has the power and precision to sniff out these faint heat signatures better than anything that has ever come before it.
So we are crossing the bridge from pure sci-fi to exploratory engineering.
That's it. It's not magic anymore. It's just a really, really big construction project.
A really big one.
But one that uses physics we fundamentally understand today. The 0 to 1 moment of finding just a single candidate that can't be explained away by dust would change human history overnight. And that could happen in the next 5 years.
So let's leave our listener with one final provocative thought. We spent this whole deep dive talking about how a Dyson sphere might be inevitable for an advanced civilization. But what if it isn't?
That's the real twist, isn't it? We assume that any advanced civilization must build these things because they'll need the energy. But what if they find something better?
Better than a star?
Well, maybe they just get incredibly good at efficiency. There's a physical limit, the Landsberg limit, on how efficient these spheres can be. But maybe they discover clean, portable fusion that's so good they don't need a star. Maybe they learn how to extract energy from the spin of black holes through the Penrose process.
So maybe wrapping a star in a giant metal ball is actually kind of primitive.
It could be like using a giant steam engine when you could have a pocket-sized nuclear reactor. Maybe the reason the sky is so dark and quiet isn't because there's no one out there. Maybe it's because the truly advanced civilizations realize that covering up the beautiful stars is a crude and inefficient way to live.
Or, to go back to the dark forest theory one last time, maybe they are there, but they've painted their spheres black, they're running cool, and they're praying that noisy little civilizations like us don't turn on a big bright flashlight and announce our location to the entire neighborhood.
Safety first.
On that cheerful note, keep looking up, but maybe don't shine a flashlight too brightly into the dark. Thanks for joining us on The Deep Dive.
See you next time.